Welcome back, everyone. I'm Michelle Sanner. Today we are going to be talking about different forms of radioactive decay. So our learning target for today is to be able to identify a few forms of radioactive decay and to be able to balance those types of nuclear reactions. But first, it might be helpful to define radioactivity. Anytime you have an emission of either subatomic particles or energy from a nuclei of an atom, that's called being radioactive. So when that is happening to a specific nuclei, we say that that atom is radioactive. Some elements are highly unstable in their various isotopes, and by emitting a small piece of themselves, either in the form of something that has mass, like a particle, or some sort of energy, like a gamma ray, for example, we say that they are able to achieve better stability. They go from an unstable to a stable situation. There are elements that do this spontaneously, and we say that those are naturally radioactive. The first form of radioactive decay we're going to look at is called alpha decay. So here we have a large unstable nucleus. It needs to emit some proton, some neutron, some form of itself in order to achieve a smaller, more stable nucleus. And we call that emission, the thing that leaves that nucleus, is called an alpha particle. These two leftovers, these two remainders, the smaller, more stable nucleus and the alpha particle, are what's known as the daughter nuclei. So another way of saying that is that when an unstable nucleus emits a particle composed of 2 protons and 2 neutrons, these are identical to helium, so you can either write that in nuclide notation as helium-4, or another way to write that is using this alpha symbol here. It's like a lowercase goldfish. Or 2. So 2 ways of writing an alpha particle. An alpha particle is a product, not a reactant of the decay process. That is to say, you don't have the alpha particle until the reaction is over. It's the most massive form of daughter nuclides, and so it can be dangerous because of its size. However, due to the fact that it has extremely low penetrating power, it's so large, it's difficult for it to fit through our tissues and through our clothing. And so it tends to be less harmful if it's occurring outside of our bodies. Alpha particles, however, when inside the body systems, are indeed very harmful to tissues. Here's an example of how an alpha decay reaction could be written in nuclide notation. So I have samarium-146. Its atomic number is 62. It undergoes alpha decay, so writing this reaction arrow is another way of saying it undergoes alpha decay, to form 2 things: an alpha particle and a new element. See, since it's lost 2 protons, it's actually changed its identity. Nd, and that is called neodymium. So this samarium has undergone alpha decay to form neodymium-142. Our next example is called beta decay. Here's an example of beta decay of a thorium-234 nucleus. You've got a large parent nucleus here, a decay event happens, and we're left with a couple of things. We're left with a beta particle and a smaller daughter nucleus. So there's a couple other things that go on, but the important thing to understand about beta decay is that you have an unstable nucleus that has emitted an electron. And I know what you're going to say. What is an electron doing inside that nucleus? Well, some nuclei are so unstable that a neutron will change into a proton. It'll essentially give up the part of itself that makes it neutral. The leftover result is something positive, and that little negative part of itself that it emits is an electron. The symbol for the beta particle can be written like this. You have beta with a little b with a little tail there. You have a -1 because it's not a proton, it's an electron that's being emitted. And up here for the mass number, the sum of protons and neutrons is 0. So that's a way of writing a beta particle. So think of it like you have a neutron. It's composed of something positive, something negative. It's so unstable that it kicks off the part of it that's negative. That's the beta particle. And it's left being overall positive. So here's an example of how you can write a reaction of beta decay. Say you have carbon-14. It undergoes beta decay to form nitrogen-14 and a beta particle. And if we check the sums of the mass numbers and the atomic numbers on both sides, we'll see that this is balanced. On the reactant side, I have 14 for the mass number. Over here, I have 14 plus 0 equals 14. So the mass numbers check out. Down below, I have a 6 in the reactant side, 6 for the number of protons. On this side, I have a 7 plus a -1, or in other words of writing that as 7 minus 1 for 6 in the total number of the protons. So this is a balanced reaction. Interesting. A beta particle is less massive than an alpha particle. It has less mass, as you can imagine, because it's basically composed of an electron, but it is a little bit more dangerous in terms of its penetrating power. Because it's so small, it is able to pass through skins, pass through clothing, and it can damage biological tissues with ease. And this is one of the reasons it makes it so beta decay so dangerous outside of the body. Our next form of radioactive decay that we're going to talk about is called a gamma ray emission. And here's a generic example of a gamma ray emission where you have an excited or unstable parent nuclei. It undergoes gamma ray emission to form a more stable daughter nuclei and some gamma ray energy. And we actually have a Greek symbol, gamma, that we use to identify this formation of gamma radiation. Notice that in the mass number and the atomic number are both 0 because there are no protons and no neutrons in a gamma ray. It's simply composed of energy. So taking a second to formally define this, gamma ray emissions are forms of electromagnetic radiation. They have extremely high energy and no mass. And because of this high energy and lack of mass, they're easily able to penetrate tissues. And these ones require very thick lead shields or concrete. You wouldn't want to encounter gamma ray emission in the wild. Often, these gamma rays are written in the form of the Greek symbol gamma. And because they have no mass, we put a 0 for protons and a 0 for the atomic number. Here's an example of a reaction that undergoes gamma ray emission. In fact, this one undergoes gamma ray emission and alpha decay. Uranium-238, so the isotope of uranium, undergoes gamma ray emissions by forming thorium-234, an alpha particle, and gamma radiation. So this is interesting. You can have multiple forms of radioactive decay within the same reaction. Moving on to our next example is something called positron emission. And in a positron emission, you have an unstable parent nucleus that decays. One of its neutrons in its nucleus basically kicks out the part of it that makes itself positive. And that little positron shoots up, and we have a little expression for that as well. So a positron emission occurs when a proton in an unstable nucleus emits a positron. It's the opposite of an electron. It's basically the subatomic particle that makes something like a proton positive. And a neutron is composed of a positron and an electron. That's what a neutron is. So basically, this neutron kicks off its positive component. It has a small mass, but an equal positive charge to an electron. And the way that we write a positron is very similar to the way we wrote a beta particle, but it has an opposite atomic number down there because it's got a positive component to it. So here's an example of writing a decay, a positron emission. We've got potassium-40 undergoes decay to form a positron, leaves the nucleus, and argon-40. So because we've lost a proton here, we can see that the potassium is no longer potassium. It's lost a positron, it's lost a proton, in other words, and that proton has become a neutron. And we've got the same mass number, But you'll notice that its proton, he's lost one proton. As that proton lost its positiveness, it became neutral, and it turned into a neutron. So crazy stuff. Our final example of radioactive decay is called electron capture. And by contrast, this is an instance in which an electron is absorbed by the nucleus, that's combined with one of the protons here. And when you take that negatively charged electron and that positively charged proton and you combine them together, the result is overall neutral. So one of these protons becomes a neutron, and you're left with a atomic number that is one smaller. So the way that we write an electron when we're writing a nuclide notation is to start with a lowercase e. It has negative a proton, it's negative, so it doesn't have any protons down below. It has no mass, so I put a 0 up above. And here's an example of a nuclear reaction that undergoes electron capture. Imagine I have a nucleus of krypton 76. It captures one electron from its orbital, combines it with one of its protons there, and you're left with bromine 76. So we'll take some time in class the next time we meet, and we'll be practice balancing and identifying these 5 different types of radioactive decay. Just make sure you've got good notes, and I'll see you next time we meet.